Today I would like to introduce the quantum cascade lasers. Quantum cascade laser is a kind of semiconductor laser with heterostructure cascade design, which consists of stacks of different materials. The band structure can be engineered by controlling the material and the thickness of each layer and adding an external voltage. As a result, the electrons can jump between the subbands and emit photons continuously. Here shows a photograph as well as an SEM image of a quantum cascade laser, and on the right shows its band structure. So what is the difference between the quantum cascade laser and the conventional semiconductor laser? For the conventional semiconductor laser, electrons jump from the conduction band to the valence band, recombining with the hole in the valence band and emit the single photon. However, in the quantum cascade laser, the series of thin layers form a superlattice, which creates a one-dimensional multiple quantum well confinement and leads to a splitting of the band structure. By carefully designing the thickness of each layer, population inversion could be obtained between the subbands, which meets the condition of the lasing. Compared with the conventional semiconductor laser, it has tunable emission wavelengths because the spectra largely depends on the geometry of the structure. Moreover, without the annihilation of the electrons and holes, the electron can emit photons continuously, which makes it have higher power than that of the conventional one. One of the most important properties of the laser is its mode selectivity. There are several approaches to achieve tunable single-mode emission. Two typical ones are the distributed feedback quantum cascade lasers and the external cavity quantum cascade lasers. Distributed feedback quantum cascade lasers are fabricated by integrating a Bragg grating into the laser waveguide. The laser wavelength is determined by the period of the grating, while the external cavity quantum cascade laser is shown on the bottom. The system forms a coupled cavity system, that is, the Fabry-Perot cavity formed by the laser's front and the back faces, and the grating cavity formed by the back face and the grating. The wavelengths can be selected by rotating the grating to reflect the certain wavelengths into the direct angle. The latter one is more commonly used because of its wider range of wavelengths. The idea of the quantum cascade laser was first proposed theoretically in 1971. However, it was first experimentally realized in 1994. The profile as well as the band structure is shown in the figure on the right, and it emits at a mid-infrared wavelength of 4.26 microns from the spectra shown in the figure. Several years later, the first terahertz quantum cascade laser was realized. For the previous terahertz generation, it was limited by the lack of appropriate materials with sufficiently small band gaps. Others are limited in output power or requires extensive cryogenic cooling. However, there is also difficulty in achieving quantum cascade lasers in such a long wavelength. It is difficult to selectively inject and remove electrons either by tunneling or scattering from such closely spaced subbands so as to achieve the population inversion necessary for GAN. The long wavelength also increases the losses due to the absorption of radiation by free carriers. However, the advantages of the terahertz quantum cascade lasers are also obvious. It is brighter than the conventional lasers. The potential applications in the range of terahertz wavelengths is also promising. The first terahertz quantum cascade laser was realized in 2001, while it was published on Nature in the second year. The figure on the left shows the profile of the band structure of the quantum cascade laser made from the gallium arsenide and the aluminum gallium arsenide. The lasing takes place at about 4.4 terahertz, which is shown in the emission spectra on the right. The development of the quantum cascade lasers in the past decades was also at a rather fast speed. For both continual wavelengths and the pulse lasers, the heat sink temperature and the wall plug efficiency both get larger. That means it no longer needs very low temperature and we can get higher optical power with the given electrical power. There are a lot of applications of the quantum cascade lasers. Here I would like to mention two of them. The first one is a high-resolution spectroscopy for sensing and measurement. The left figure shows the photoacoustic spectrometer for trace gas sensing of benzene. The quantum cascade laser emitting at the wavelength of 14.8 microns is used as the light source, of which wavelength contains the strongest vibrational band of benzene. The photoacoustic signal is shown on the right, comparing with the signal of the nitrogen and the carbon dioxide. Another application is a high average power source for imaging. The laser used in the experiment has a peak power of 50 milliwatts at 4.3 terahertz. The experimental setup and the image is shown in the figure. It achieves a signal-to-noise ratio of 340. Besides the following ones, there are also a lot of other applications such as the frequency locking, phase locking, and the nonlinear mixing of terahertz quantum cascade lasers with near-infrared radiation. Finally, let me focus on the outlook of the quantum cascade lasers. The tunable wavelength is one of its most important advantages. From the tendency, we might predict that there will be lasers developed for a wider range of wavelengths in the future. However, there are also challenges. The first might be the temperature. It is hard to obtain a high efficiency without low temperature. However, it is not an important drawback, and as shown in the previous pages, the properties at high temperature of the quantum cascade laser is improving year by year. The power and power efficiency is also an important topic. There is still a long way from the laboratory to the consumer electronics. Those challenges leave a wide range of topics for the future research in this area. That's all what I would like to share today. Thank you.